In this video, we're going to talk about complex number in polar form. Now, I mentioned this once or twice over the last couple of videos, but basically what it boils down to, we have these two numbers here in the traditional sense we've been writing them. We're going to name that now, we're going to call that rectangular form. Not too important, there is a rectangular form. It's not too important, but this is one of the ways we've used them for now on. We're going to go on to using them in this sort of form. So let me just write that a bit more formally here, the two forms. We've been used to writing it a plus ib. That's where, and it helps really to look at it in the drawing of these questions. So in this sort of sense, we go out a number, and let's take this number here, minus 2 minus 2i. We go minus 2 minus 2, and that's how we draw a point. We get the number down here, and we can draw it. In the polar form, it's a little bit different. This is all the information we need. This one here is more classical, how it's written. We write the radius number out front here. In this case, it's the 1. There's a 1 out front of both of these. It's just, it's not written there to save a bit of time. But honestly, let's actually put it in. Let's put it in just to make it a little clearer. Rub that out and we'll put a 1 here. I hope you can just about see that. So this would be polar form, where it gives a radius and an angle. The same angle here and here. It's cosine an angle plus I sine an angle. Cosine an angle plus I sine an angle. That's in polar form. Let me write it a bit more formally. Or, for radius, multiplied by cosine theta plus I sine theta. And so this is the one we're going to learn more about today. How I'm going to teach you is by just giving you a couple of examples of the old style number and writing it in the new style. Because we can change. They're just points. If I give you any point on a screen, it might seem easy to give me this form here. That's because we're used to giving these ones. We go, what, about 2.1 minus 1.8i. We're used to doing these ones. But this new form, what we're going to say is, we're going to say an angle. So the angle here, I know, I'm guessing again, just like I guessed with the numbers, I'm guessing here the angle in here will be about 40 degrees. And the length, the distance from here to here, about 3, I'm not sure, well, I'm guessing. We're going to do it more formally and a bit more maths. 2.7, something like that. So either of these forms are fine. I'd have to guess with either of them without doing maths from just a little drawing. But we're going to do it a little more formally. We're going to change this guy into the polar form from here to here. Number 2, we're going to change from rectangular to polar again. Question number 3, we're going to change from polar into rectangle. And number 4, we're going to change from polar into rectangle. Why are we doing that? That's one of the big questions students usually ask. Why am I doing this? I know how to do this one. Why do I need to do this one? Well, actually, as it turns out, it's easier, this second one, for lots of questions. It's easier for getting the square roots, for getting the power of numbers, and we'll see that as we go forward. It's not too difficult to multiply either. I would say it's probably easier to multiply using this form. And then it becomes more useful for modeling certain things in physics. Rotations come out a lot easier in this. This is actually one of the reasons we use complex numbers in other things. Rotations come out in some questions, and polar coordinates are good for dealing with rotations. It's not just in complex numbers either. We use this same polar form in coordinate geometry instead of our classical, like you're fairly used to using this form, x, y, but there is another form, or theta. So you're going to learn about that in future. So we might as well start learning it now. Okay, let me jump right in and start answering some of these questions. Question 1, I'll use this drawing here to help me with a lot of these. We start with the minus 2 minus 2i in rectangular form. Let's draw this on the picture here. Minus 2 minus 2. Here is in rectangular form. Now, how we draw it in polar form is simply, let me draw a line in here. Oh, that's a terrible line. I'm sorry about that. Draw a line in here. This is nearly everything we need for a polar form. The or out front, let me write it up here, or cosine. I shouldn't have rubbed it out really. Or cosine theta plus I sine theta. This is the polar form. The or is simply the length of this line here. That is what, so I need that. I just need this length of the line. The theta is this angle here. I need that angle. And that's really all this question is now going to ask us. There are, you'll see some formulas, basically how to do this really quick, memorize a formula. I don't like that. I think we can just learn how to do it each time. It's not too slow. And once you get the hang of this, then you should be able to figure out the formula on your own without anybody ever showing it to you. So okay, so remember this guy down here is 2, 2. I need to get this length or. So let's have a look at this triangle here. Or this triangle, either one really. Let's take this top one here. Let me draw it out again. This top one here. This length is 2. The height there is 2. This length over here is 2. Minus 2. 2. Can't be minus 2 in a length. So I just need this length, and that is 2 squared plus 2 squared. 4 plus 4. That's the square root of 8. That's Pythagoras theorem. 2 squared plus 2 squared. The square root of 2 squared plus 2 squared. Square root of 8. We have or. Now, the other thing I need is this angle here. This angle here. I need to get it. This is 180 plus another small bit. That's how I get this large angle. Or if we're using radians, this is pi plus a small angle. How about I do the first one in degrees and the second one in radians. Let me put a D there and an or there. Let me put a D and an or. Actually, sorry, this is already in radians and this is already in degrees. So let's do this first one in degrees. That means 360 degrees in a circle. The second one we'll do in radians. That means 2 pi degrees in a circle. Okay, so I need to find this angle here. We'll call it theta for now. Well, that should be easy enough to get. That's tan of theta is equal the opposite over the adjacent. 2 over 2, which is equal to 1. So theta is equal to the inverse tan of 1. And what is that? That is, you can check on a calculator, but that is actually 45 degrees. And that shouldn't be a surprise to us, because it was 2, 2. It was the same distance out as the same distance up. We would expect to get a 45 degree angle. But don't worry, put that in your calculator. Check your formula table. When is tan theta equal to 1? It'll tell you 45 degrees, or the calculator will tell you. But yeah, I would like students to notice that 2 and 2 will give 45 degrees. So this is enough. They gave us the question as minus 2 minus 2i. Well, that's the same as writing square root of 8 or cosine angle. What angle is it? 45 degrees? Not quite. 45 plus 180, which is 225. So I'm just following from here really, plus I sine, and again 225. That's it, yes. This is the answer. This is the answer for part 1. So it's really just about figuring out this triangle, and all 4 of these are going to be figuring out these triangles. That's the secret to this. That's why I think students are crazy trying to memorize a little formula. It's a little question that they will be asked in other questions anyway. You need to know how to manipulate triangles like this. So you might as well learn it this way. We just have to play around with this triangle and get the length and the angle. That's it. There's our full answer. Let me rub this out and we'll do part 2. I'll clean this up a little so we can put it in. Okay, here's part 2. We're going to do this the same way we did part 1, with the only difference being we'll do it in radians instead of degrees, which won't be too big of a difference. If you're unsure what radians and degrees are, hopefully this will explain it a little bit, but we'll have another class on that entirely at some future date. I don't have it up at the moment. It might be if you're watching this video in the future. Okay, so the same way we did before, let's draw this in. Square root of 3 is about, I don't know, 1.5, 1.6, but let's just double check what it is. Square root of 3 is 1.7, somewhere about here. And then one that is. Remember, there's always a little invisible 1 in front of things like that. So we're about here. Here is where this number is. This is what this number looks like on an Argand diagram. But it also can be wrote in this form, where or is this, and theta is starting at the x-axis and moving around. So theta is just this here. So this one's a bit clearer to see than the first one. So we just need these two numbers. So let's try and do that. We'll do it separately over here. Here's theta, here's or. What do we know? We know the height is 1. We know the length here is square root of 3. So I just need to get or. Or is equal to the square root of 3 squared plus 1 squared, all the square root of it. Square root of 3 squared is 3. And 1 squared is 1. Square root of that, which is equal to the square root of 4, which is equal to 2. Or is equal to 2. Let's write it there. Or is equal to 2. Okay, what else do I need? I also need the angle. We have lots of choices now that we know this is 2. But let's use what was already there. And we have the tangent of theta is equal 1 divided by square root of 3. Now, let me do the next line first. Theta then is equal the inverse. Let's just destroy the tan. What destroys the tan? The inverse of a tan. Same thing that destroys everything. Inverse of multiply destroys multiply, which is divide. But the inverse of tan, 1 over square root of 3. This is a famous number. You can check your formula tables. The tan of theta gives you 1 over square root of 3. What is theta? But don't worry, if you don't know, we can also just ask a calculator. Now, I'm in radians, so make sure your calculator is in radians. And be careful putting it into the calculator. But the calculator gives me out the answer 1 over 6 pi. If you were in degrees, it would give you, remember, pi is the same as 180 degrees. So if you were in degrees, it would give you a 30 degrees. But we don't want degrees. I asked for in radians. So this is the answer. Or we could write this as pi over 6 is usually a bit more. I just wrote what the calculator told me. The calculator told me this. So pi over 6 is what I'll go with. That's it. We're already finished. I can already write my answer here. This is equal to or. Where's or? Or is 2. And cosine. Theta. Well, here's theta here. I just found it. It's pi over 6 plus I sine theta. Well, I just found it. Pi over 6. That's it. That's the same as this question. The same as writing square root 3 plus I is 2 cosine pi over 6 plus I sine pi over 6. I know this looks easier. I know this looks shorter. I know it looks crazy to write the answer like that. But it is helpful for so many different things. And for example, look at this question. Square root of 3. I hate square root of 3. It wasn't exact, was it? It's 1.72 blah blah blah. It goes on forever. It's a horrible number. But look in this world. 2. That's not a horrible number. Pi divided by 6. Not horrible. Okay, yes, pi is a horrible number. But remember, in this world, this is just 30 degrees. Pi over 6 is not a horrible number anymore. Using pi as radians is not horrible anymore. All of these are solid numbers here. And yes, if this was in degrees, it would be just 30 degrees. All solid numbers. So there is a reason to use polar coordinates sometimes. Alright, let's move on to part 3 and we'll see how to change it back the other way. Okay, here's part 3, and although it doesn't seem it, we're going to start this the same way. We're going to draw it first. Let's put in a rough drawing of this question. Now, in all of these, you do not have to draw them. I just think it's always helpful. Just a quick little axis, rough numbers. I used the ruler to draw the 2 lines. Other than that, I just roughly did it all. That was a good catch. So we're going to do this just the same as before. Now remember, we might have to just add in a 1 here, just because it didn't seem clear that there was a 1 here. So from this, the 1, remember, is the radius, the length. The angle here, pi over 2. Now pi over 2 is half of this line. This is 0. This is pi. Pi over 2 is the same as 90 degrees. Pi over 2 is straight up here. So now we have an angle and we just need a length. 1. This is going to be the shortest question. This is just the angle 90, the angle pi over 2, and the radius 1. And where do we end up? We end up at I. So I can just write the answer at this. I don't need to do anything. There's no triangle involved here. It works out quite nice. It's 0 on the real line plus 1i. Or to write that a bit more neatly, just I. That's it. That's all. This whole thing could be wrote as I. And that's part 3. There's part 4. We'll do a little more like part 1 and 2. We'll get a triangle. But in this case, we didn't have to do a triangle. It was just neatly on the line. Once again, let me rub this out and we'll do part 4. Here we have part 4. This time they've given us degrees instead of radians. So lots of students hate radians. They like degrees because they're used to them. I'll say you should hate degrees and like radians. Radians are the perfect thing. If we met aliens from another planet, they'd understand radians. They wouldn't understand degrees. We just made up degrees. Why is 360 so special? There's nothing special about it. Pi, there's something special about it. Okay, but forget about that for the moment. It doesn't matter when going this direction. Let's start this like we did part 1 and part 2 and even part 3. Let's draw it. Okay, we get an angle and we get a radius. The angle, remember, is starting here, tells us which way to point. So let me go through here. 0, 45, which is what we want. 90, 135, 180, I'm not sure, 270, all the way back to 360. All right, so what do we have? We have 45 up here. Let's draw in a rough line there. And we have a length, square root of 2. Again, check that on a calculator. But the square root of 2, I think, is... One moment, I think it's 1.7 maybe? 1.4? Let's find out. It is 1.41. So get a ruler if you want a rough answer. It's not going to be too important, but 1 is here, 1.4, I'd say around about there. Actually, I know it's going to be very close to around about there. So that's where our point is. But remember, we want to write this in the form of A plus BI. A plus IB, or, well, BI, I guess. So again, let's just draw ourselves a triangle. I don't know where this hits. I actually know it should hit the 1, I think. But we'll come back to that in a minute. Let's just pretend I don't know. I draw a rough number. I don't know where it hits here. Let's draw that triangle, okay? Here's the things I know. I know 45 degrees, and I know square root of 2. I don't know this number. I can guess from the drawing. Maybe it's 0.9. The drawing here, maybe it's 1, I'm not sure, but I can from maths check, because this is a right angle. There's 3 things I know about this triangle. I can get everything. Okay, so I want this number, because that'll give me the A here. I want this number here, that will tell me the B. Okay, so let's just go ahead and solve this. We need something with this number, with the hypotenuse and an angle. Well, that would be cosine of 45 degrees should be equal to the adjacent. Let's put in an A here and a B. You can use X's, Y's, anything you want. Should be equal to A over square root of 2. Right, let's just solve this. That's square root of 2 cosine 45 is equal to A. And if we put it into a calculator, square root of 2 cosine 45 degrees, we get out 1. A is equal to 1. That is 1 length. And the drawing looks about okay for that. Remember, I didn't use a ruler, I didn't measure it. But if I had it would have looked quite good for 1. You can't take the drawing though. You do need to do the maths. This is exactly 1. This answer here is exactly 1. Okay, now I need to get the other one. Let's see, I have an angle, I need the opposite, and I have an hypotenuse. Well, that is the sine of an angle is equal to the opposite over the hypotenuse. So if we rearrange that, square root of 2 sine 45 is equal to B. Let's do this one without a calculator. Let's pretend we have our formula book. They tell us what sine of the famous angles, sine 30, 45, 60, 90. Sine of 45 degrees comes out as square root of 2. Sine of 45 degrees comes out as 1 over square root of 2, which is equal to 1, which means B is equal to 1. Which means this whole thing here is equal to 1 plus 1i, or I. 1 plus I. Okay, so that's how we change between them. Hopefully this doesn't seem too complicated. It's not meant to be outrageously strange. It's meant to be quite easy to do after a while, to change from polar coordinates to rectangular coordinates. And it's useful. I promise you it's useful. We'll start to see why in the next video. We'll start to multiply these type here, the polar coordinates, complex numbers in polar form. We'll start to multiply these together and we'll see, oh, you know what, that is actually a little easier to do that way. Maybe you won't think that, but it'll be a little different anyway. Hopefully you'll find it a little easier for some questions. Questions with square roots here, it tends to be a little easier. Also then, in a video after that, we'll start to do powers. If you wanted to get, let me just do a little example just right here. So 3 plus 4i to the power of 17. I'm guessing you don't want to do that. I'm guessing that would be difficult to multiply out. Forget 17, even just 7. Do you want to do that? You'll be there half an hour. Not in polar form you want. We're going to teach you how to do in polar form and you'll be done in a minute. It's very useful for some things. Okay, hopefully you stay with me for those, and thanks for watching and goodbye.